session, which is open pit, civil and natural slopes, and that's going to be chaired by Tom Stiles and Navid Briani. And I believe that I will be just handing over to them. That's correct, Yusuf, isn't it?
Exactly. Yes, Julian. Thanks, Gary. Yes, I think right now Navid is going to read Tom's bio and then going to start the session.
Yeah, thank you. Do you hear me well?
Yes, Navid.
Thank you. My name is Navid Barani, and I am a professor of mining engineering at Dalhousie University in Nova Scotia, Canada. Welcome to the first technical session of TMIC 2022, which is on pit, civil, and natural slopes. So I'm co-chairing this session with Dr. Tom Stiles, who is going to be our first presenter. Tom is a chartered engineer who has been working in mining for 17 years, completing a PhD at Camborne School of Mines on numerical modeling of fractured rock slopes. Following this, a postdoctoral research at Simon Fraser University using INSAR and numerical modeling on large open pits. Since 2010, he has been a geotechnical consultant for mining projects and operations, working on site collecting geotechnical data and off-site completing analysis. Tom joined Cavrock in 2019 and Mining One Consultants in 2020, focusing on numerical modeling for large-scale open pit and underground operations. So I'm going to ask Tom to start his presentations.
This is really quite a generic talk, really. More to sort of introduce the session and start the people thinking about numerical modeling of, in this case, large open pits, rock slopes. I think in the title I actually had underground mines in there, but I've tailored it again back to being rock slopes in following the theme of the conference. So I'll briefly just talk about numerical models. Why do we need them? What's the aim of modeling? And then briefly I'll go over the approaches, so continuum and discontinuum, and then that'll lead into the rock mass criteria. So that's specific, particularly important when you're looking at large open pits, and understanding rock mass damage, of course. So. And then there's an approach that we recommend, and I'll just provide some examples as we've touched on already, actually, in this. So the objective of numerical modeling, I quite like this this quote here, in that it's an aid to thought rather than a substitute to thinking. So as Gary has said, it should really, when someone presents you with an idea from a model, it should start you thinking. And if you have another idea, then you can take the ideas from that and lead into your ideas. It's really a tool, and we can use that tool to obviously investigate theories and on failure initiation, and also guide your rock mass classification efforts. So you can reveal which inputs using sensitivity analysis. You can decide which inputs have the greatest influence, and you can justify then the focus for certain aspects of rock mass classification. And it really does allow you to test the design prior to implementing, as Gary has mentioned there. So one of the quotes from Hook is quite good, that it should always be referred to as an approximation to reality, but I think what's quite key is that it needs to be as close as representation to nature as possible. So you need to make sure that approximation is, you haven't got too much fudge in there. Try and get it as close as possible. So we've heard a bit about the economics. This is just a couple of simple images just to show what the main impacts are on an open pit. So in an open pit, if you have a larger footprint of the mine, obviously you have a significant increase in the stripping ratio, and in the case that Gary presented, if you've got a step out in the base or in the wall there, then you have a decrease in recovery with sterilized ore. continuum discontinuum approaches. I think it's generally widely accepted that there's 3 scales of study when you look at slopes. You've got the small scale, which tend to be quite discontinuity controlled, and then at medium and large scale, you tend towards a more mass or continuum control behavior, and that's really the complex interaction between rock strength and the fracture network. So incipient joints and bedding. Another name for this mass controlled behavior is equivalent continuum. And an example of an equivalent continuum approach is, say, the synthetic rock mass technique, which Itasca actually use. And that's where you're actually directly calculating the scale effect. And this graph here shows that scale effect going from your intact strength right down to what your rock mass strength will be at an overall scale. So there's 3 levels of sophistication when it comes to modeling. You start with the first approaches, which are limit equilibrium or kinematic techniques, and then the second and third techniques is what I refer to as numerical modeling. A lot of people kind of consider limit equilibrium as numerical modeling as well, but I think really numerical modeling should be kind of kept for those approaches which are mesh based and use you know, resolve stress, strain, and plasticity in them. Whereas limit equilibrium, you know, you're essentially resolving the driving resisting forces, whether a slope is in equilibrium or not. Okay, the rock mass strength criteria is particularly important when you're considering that larger scale. I think it's very widely accepted that we use the Hook-Brown strength criteria, and that reflects pre-peak, pre-yield strength very well, but it doesn't consider any post-peak strength. I'll just set this little video playing here. This is I think something that Abu had in one of his talks actually that I quite liked. It really does show that pre-peak behavior quite nicely. So you have the elastic. This is a spring, if you like. So it shows the elastic recoverable straining on the spring once you get up to this first point, and then beyond this, you're entering the plastic realm, and it's there where you start to go past your yield point is particularly important in rock masses. And I think in all large open pits there is some degree of movement and enclosure, and that's a natural response to mining. But I think in mining, which is different to civil, we do tend to be closer to that yield point. So I think the rock mass behavior is mostly beyond that yield point. You know, we are looking at conditions which are quite complex. So having a constitutive model that actually represents the rock mass strength beyond the yield point is particularly important. Sometimes, you know, we may be dealing with a rock mass that may be in this primary stage of motion, but in any case, there's still this time-dependent progressive behavior that needs to be considered, and that's where this the approach that we use, the improved unified constitutive model, comes in, and that's been used for more than 7 years, and it provides the full response of the rock mass. So you one of the most important things I think for certainly for open pits is the D factor, and you know, there's different guidelines to how we apply it, but it's pretty much a guess work. So having a constitutive model that actually takes that away, like IUCM, it explicitly considers that stress relaxation part is really key, I think. Okay, this slide here just talks about the importance of understanding the complexity of rock mass. And we've briefly heard, I think Gary mentioned anisotropy. And this is actually often overlooked. It should be considered separate to GSI. And really, when you have a very highly anisotropic rock mass, you can consider the rock it be quite complex. So this may, in this case here, you've got a high GSI and quite a high MI. But you know, having a more conventional approach, say a limit equilibrium or approach, it can't consider that, it can't capture that complexity. So you know, using a more robust solution is important. And these images here just show the anisotropy. So in a bedded unit, you may be looking at the rock mass anisotropy, but it's actually should be captured by the GSI. But in a more foliated unit, you really do need to capture that anisotropy at the rock mass scale, because it controls the possible failure mechanisms and the redistribution of stress.
There's 3 minutes left, Tom. Sorry to interrupt.
Okay. Thank you. I'll just skip through these a little bit quicker. So the volumetric strain is a way that we can quantify rock mass damage. And in open pits, this is particularly important because we can use the higher volumetric strain to correlate well with different rockfall locations. The tool that we've mentioned, SlopeX, it uses the FLAC 3D solver, which is quite, long recognized as a robust solver, but it makes it accessible. So, you can run many design iterations, and then it obviously links in with the improved unified constitutive model. Just to give you some examples, in a 2D case, this is some charts that I've started to develop, where you can basically, using SlopeX, you can run a lot of models very, very quickly, and you don't have the D factors. So you can come up with some answers for a particular rock mass quickly, and then you can derive the different the slope height, slope angles relationships for that particular condition. And in a 3D case, I think we've just seen these examples here from Gary's talk. You can use the approach to really quite achieve quite a detailed calibration in your model and back analyze slope failures effectively.
Just 1 minute, Tom.
Yep. So in summary, really, I think extractive companies are becoming more and more aware of their social license to operate, and there's some important sort of stakeholder engagement. And if you have a large slope failure, not only is it hazardous, but it's also bad for public image. So I think using your the most advanced tools to provide a most realistic solution is getting more and more important. I've talked briefly about the different methods, and I think capturing that complex ground condition, representing it effectively is very important. I think really being able to investigate instability and efficiently and test designs prior to implementation is paramount. So that's all I've got, actually.
Thank you very much, Tom. Due to time limitations, we have to move on to the next speaker, and I'm going to ask you to introduce the next speaker.
Sure. Just stop sharing.